wearing masks all day long for weeks and weeks. It's terrible. Anyway, I'm honored that you all stayed and came to this lecture this evening or afternoon. We'll try to make it as entertaining as possible. Okay, so I'd in fact like to go through quite a bit of material, so I'm going to just move relatively fast and stop me if you're wanting some more explanation. I'd like to get all the way through proximal point algorithms and extra gradients and show you proofs for all these things. And then I'd like to then return to the mechanism design things that I started my lecture series with. Okay, so we're in the world of variational inequalities at this point, and that's a very general formalism and a lot of mathematics for it. But like I said, it's kind of like 10 years ago in optimization. There was a lot of results, a lot of huge literature, but some questionable relevance, and it was a big opportunity to add kind of non-asymptotic, high-dimensional, stochastic kind of ideas to that literature, and so there's some of the same opportunities here. And as far as I'm concerned, the applications are even broader and have bigger implications. So I think for all of you in the audience, this is a real opportunity to get into this. At the end of the lecture, if I don't remember, remind me, I'd like to write down a couple of references that for you, because you could follow up and read it more slowly at your leisure. Okay, so it is a huge literature, and it's a lot of math, and it's math. It's written for mathematicians, so it's just kind of starts out with, let B be a Banach space, and let this operator, and blah, blah, blah. And there's then hundreds of pages like that. There's never a figure. And so I'm going to try to add figures and to kind of emphasize those and emphasize a bit of intuitions and give enough of a proof, however, to kind of nail something down while leaving maybe a couple of details. So to kind of do this, to make this possible, I'm going to focus on kind of two vector fields. One is this one we've already kind of spent all of our time on, but we will still have it in mind. And the other is the circular flow. Okay, and then there's multiple of these. So we like methods that apply to both of these situations equally well. They don't know which situation they're in. And we like to find, there's no notion of optima here. There's equilibria, there's other kind of concepts, but those are all fixed points. So we want to find fixed points of operators. That's the general framework. And optimization and convex and concave and all that, non-convex constraint nests within that. So fixed points is kind of the general formalism. And so in particular, this would be a fixed point of this flow. If you start there, you won't move. And similarly here, right there, that guy is a fixed point of the flow. If you start there, you won't move. Okay, now, do you want to be there? Well, yeah, that's a Nash equilibrium, for example, in game theory. So this would be, if I were to make a drawing of, it's not a vector field, a gradient field, so there's no potential function line behind this. But what there is a pair of functions for the two agents in the problem, and for the zero-sum game, one of those functions is f of the two variables, and the other is negative f of the two variables. Okay, and so one person's wants to go up, and the other wants to go down, and this is a point where they're both simultaneously don't see any possibilities for improvement given what the other player is doing. So this is a saddle point of that function f. Okay, so you can imagine that function f, if you will. All right, so and then that flow arises from that by the gradient and the negative of the gradient. And so the general Nash equilibrium is just that extended to n agents. So every agent, you're at a point where every agent looks in the direction in which they can move, and they say, I can't improve in that direction. So kind of think of something like this. I can't improve, and everybody agrees on that. And so somehow they got to this point, and they're all kind of as happy as they're going to get. And originally Nash, proved this partly for behavioral reasons. He wanted to explain why people do what they do. He says, well, they're in this kind of equilibrium, and they don't know, I don't know how they got there. And so for years, people just proved properties of these equilibria, and they didn't think about algorithms to get there. Okay, and then the optimization people kind of said, well, we know how to kind of do things like that, and they started to prove things about these flows. Okay, all right. So one of the big ideas they started to work with was something called a monotone operator. Okay, so this kind of generalizes convexity, and it applies, however, to these flows. And so f is a monotone operator if inner product between f of x minus f of y, and don't think gradient here, think this diagram if you're kind of having trouble with moving beyond. So that's monotonicity. We'll occasionally be interested, but not so much. By the way, this is for all x and y in whatever constrained space, which is usually a convex set that we're interested in. And so strong monotonicity, sometimes the overall problem isn't strongly monotone, but some part of it is. And some of the more advanced literature, which I probably will get to today, kind of tries to break problems into pieces. Here's a strongly monotone piece, here's a not, and then put solutions together from the different pieces. Okay, so this is kind of like strong convexity, so you're going to get a term on the right-hand side which is bigger than 0. So f of x minus f of y, x minus y, greater than or equal to some mu x minus y squared. Okay. Okay, so this definition applies equally well to here and to here. Okay? And if you want to think through that a little bit, it's useful. Here, this inner product is going to be strictly greater than 0 at all for all x and y. Here, it's going to be greater than or equal to 0, but mostly equal to 0. Okay? You're just getting this rotation, and so the inner products are preserved. So somehow we'd like to get arguments that work for both of those cases, and that seems challenging. Okay, so I'm going to try to give you a little more geometry, and the way I'm going to do this is I'm going to start off with doing the naive thing, which is just say, okay, we know how to do gradient descent, and it works for problems like this. Does it fail over here, and kind of why does it fail? And can we say a little bit more, what's the mathematical reason? And is it possible that strong monotonicity, which kind of, seems to give us a little extra boost, it's possible that that can actually make it work over here. And what rate would we get if it does work? It is going to work, and I'll give you the rate. And I want to get you the rate. And the rate's interesting because it's going to be pretty good. It's going to be a linear rate. It's like what you get for strong convexity in optimization, but not quite as good. And there's something missing even if you have this strong monotonicity. And that thing it's missing is called co-coercivity. And we'll talk a little bit about what that is. Right. So, okay, so let's consider the iteration. Again, I'll call this a naive algorithm because it's only going to work in some cases, but not in general, which is x of t plus 1 is equal to some projection onto the set x. I'm going to mostly be ignoring this for the rest of the lecture just to keep it simple, but I'll mention how you handle it in most cases. And then x xt minus alpha f of xt. Okay, so take wherever you are, treat this as if it was like a gradient. It's not, but pretend for a moment it was, and just go downhill a little bit by an amount alpha. And once you've done that, project on the set x. All right. Now a fixed point will be if I plug in x star on both sides. This thing will define a fixed point. This will not move if you're at a fixed point. The question is going to be, do you converge to these fixed points? Okay, so this guy right here is not going to be at all hard to handle, and if I get there later, I might show you how you do this in general. Basically, when you do these x of t minus plus 1 minus x of t squared, to try to then expand that and get progress, you have a difference between projected things. Projection of something and minus projection of something else. Projection is the contractive operator. Okay, so that thing is greater than or equal to the arguments, the difference of the arguments. So you throw away the projection at the expense of an inequality. All right, now that doesn't quite work in our more general settings like this, but there's something else that does, which is that the projection operator is not just contractive, it's what's called firmly non-expansive. So if you've read Boschke and Combet or whatever, you'll learn what that means. It's a little bit stronger, and that little bit stronger is just what you need to do what I just sort of said. You'll always be able to get this inequality. Okay, so this thing we can just kind of basically ignore. Okay, so if we don't have a constraint set like we didn't have in these diagrams over here, then without loss of generality, we can assume that f at that fixed point, this is x star, f at x star is equal to 0. Okay, well, and in fact, it's not just without generality. It's implied by the variational inequality framework, because the variational inequality says that f of x, inner product with x minus x star, is greater than or equal to 0 for all points in the constraint set. Well, if the constraint set is everything, that means that all directions, which is the usual variational picture, all directions, you're a stationary point. So f of x star has got to be 0. Okay, so in a lot of what we're going to be doing now, f of x star will be equal to 0, and that's just because we're doing the unconstrained case for simplicity. If you have the constrained case, we know how to handle it. All right. So let's draw a picture here. Here's x star sitting over here, the thing we'd like to converge to. Here's some x where we currently are. And what monotonicity says over here, if y is taken to be x star, that thing will vanish. And so we just have f of x comma x minus y is greater than or equal to 0. And that picture looks like this. It says that the inner product between this vector and f at x is positive. And so then if I take negative of f of x, this angle, let's call it theta, is acute. Okay, so it's another way of writing what this says. So that's interesting. Now it's acute, but it could be because of this greater than or equal to 0. It could be a right angle. And in fact, it is in that other diagram over there. Okay. Now if it's really acute, like it would be for under this assumption, then it kind of immediately shows you that if you follow this dumb, naive algorithm, you actually make progress, that this distance here is less than this distance. Okay? So it kind of seems pretty easy. But what if it is 90 degrees? Is there anything we can do in that situation? All right. Another kind of way to look at this exact same geometry is to, first of all, fix x, consider f minus f of x from that. The monotonicity condition says that x star, the other variable in the problem, is in this half plane. Anywhere up here. Could be on that line. Okay, and then strong monotonicity says that x star is actually, there's a quadratic there, given by this, and you're on this side of that quadratic. Okay, so that both those two geometries are going to be helpful to us here. Okay, so let's do a little proof, sort of get used to these kind of proofs. So I'm going to be using strong convexity here. So I'm sorry, strong monotonicity. Okay, so let's assume strong monotonicity. We're in this situation, but we're going to see at some point where if we didn't assume that, we only assume this, where we'd mess up. Okay, so let's just start with our usual argument. How far are we from the optimum? We put in the dynamics, and let me put in the projection. So we have the projection onto x of x of t minus the naive step, like that. All right, minus x star. Now x star is a fixed point of this operator, so I can actually put the operator in. So to make this look like this. So if I project onto x of x star minus alpha f of x star, okay, that just gives me x star back again, and x star is in this set, so I just get x star. Okay, it's just a complicated way of writing x star squared. Okay, so I've got pi x of something minus pi x of something else, and kind of the picture is here's a convex set x, here's something else. When I project onto x, they only get closer. Okay, easy little proof. Again, in general, because of this greater than equal kind of thing, we're going to need the strong, or so the firmly non-expansiveness, but we'll talk about that maybe later. So this is then therefore less or equal to, you can erase these, and we get the differences inside. So it's xt minus alpha f of xt minus x star plus alpha f of x star, quantity squared. All right, and then just the usual things. We expand out these quadratics, putting terms together we know they're going to be helpful. So this is equal to xt minus x star, because obviously we want to match up to this, minus 2 alpha xt minus x star, inner product with the f's, f of xt minus f of x star, and then a alpha squared term. Okay, now if we only had, so the middle term in the previous arguments was controlled in, with smoothness or with strong convexity. We're now using monotonicity. And so monotonicity is a condition on inner products between the vector field and the variables. So it looks like it's primed, ready to go for monotonicity. Okay, and it is, but if we use just monotonicity, this would be greater than or equal to 0 with the minus sign less than or equal. So we would get an inequality where this thing would just disappear. And that would be bad. Because we would then, get out of, say, Lipschitz on this. We're going to assume Lipschitz. Then we would get this term goes together with this term, but there's a expansive coefficient there. Right? So that would be a problem. So somehow we need to retain this thing with that negative sign, that key negative sign there, to kill off enough of this so that we don't expand. Okay, it's a pretty simple idea. Okay, so we just kind of realized that this thing will not work. You can go ahead and finish up the little calculation and you'll see that you'll get an expansive term. And so we think, what about this? All right, so we put in strong monotonicity and we get less than or equal to xt minus x star quantity squared minus 2. What did I do? No, I'm here. Okay, minus 2 alpha mu norm of xt minus x star squared, so I'm just using that, and then plus alpha squared, same thing. Now over here, what I'm going to do is I'm going to make another assumption. I'm going to assume Lipschitz flow. Okay, and that's a very common assumption. We already used that last time, and if you don't have kind of Lipschitz flow, if the flow can have real kinks in it at all, it starts to get to be like fluid mechanics or something. It's really hard to say what to do. So we're going to assume Lipschitz here, and so I'm going to pull out an L squared here, and then I'm going to get the difference of the arguments squared. Okay, that was Lipschitz. And now you can see what's happening. I've got a whole bunch of xt minus x stars. That's pretty nice. And if I put them all together, I get less than or equal to actually. So first of all, let's now, at this point, we kind of know what alpha we should choose. So let's set alpha equal to mu over L squared. When we do that, we're going to get, 1 minus 2 mu squared over L squared plus mu squared over L squared times this term. And that's equal to 1 minus mu squared over L squared times this. Okay, so this is our final rate. So this is a rate. We're knocking off this factor every time from the error, and so we'll do that, some logarithmic number of times to get down to some 1 over to some epsilon. Okay? Now, interestingly, so first of all, we couldn't get anything if we just assume this. We put in this nice, strong assumption. We go all the way to a linear rate. Okay, so it's suggesting we still haven't really explored the terrain very well here. But also there's a interesting little issue here, which is that the rates we get in the optimization world when we put in these strong assumptions like strong convexity are 1 minus the condition number, mu over L. Here it's 1 minus the condition number squared. Worse. Interesting. All right, and so where did we lose something here? Well, in some sense we didn't lose anything, because strong monotonicity alone is not enough to get us all the way to that faster rate that we see in the optimization land. Okay, and so what's missing? What do gradient fields have? They are actually strongly monotone, but they must have something else that's missing from the general story. All right, and that something else is called co-coercivity, and I'm not going to spend any more time on it. I'm just going to define it so you know what it is. And I have some papers on it, and many other people do too in the optimization literature. It is worth knowing about and following up on at some point, just not today. So co-coercivity is just another one of these ways to control inner products. So it's kind of a dual way to do it. So it's this thing, x minus y, is greater or equal to f of x minus f of y squared. Okay? If you had an x minus y squared over here, that would be called coercivity, and that's equivalent to strong monotonicity. This is co-coercivity because it's working with a dual quantity, not the x's but the f's. Okay, and so you can prove, it's a nice little proof to show that gradient fields obey this. And because they obey this, you can use that in that proof and knock off that term, knock that down to 1 minus mu over L. So nice little exercises for the reader. Okay. Yeah.
So you can use strong monotonicity as having a Lipschitz lower bound on the f of x. If you use Cauchy-Schwarz, you get like.
Yeah. So what this is saying is there's a gap between Cauchy-Schwarz and what it bounds. That little in that gap lives co-coercivity.
Okay.
Yep. Exactly. All right. With that as background, let's now jump to the newer ideas. Let's jump to the proximal point algorithm. Okay, so the way this is often taught, it's maybe someone knows a particularly nice place. I've not found a great place to learn about it. Usually it's just here's the algorithm and then here's a bunch of analysis. Or if it's an optimization book, so my favorite optimization book is Amir Beck. If you haven't seen this one, it's a beautiful treatment of linear optimization. It has a lot of the key ideas in there. I would recommend it highly. But there's a little section on the proximal point algorithm, which I'm kind of highlighting. It's very important. It leads you to all this other literature. And he has half a page on it saying, this makes no sense. Why would anyone ever do this? Okay, so it's kind of interesting. And I think you'll see why. But anyway, here's what I want to. I'm going to do this in a way that I haven't seen in the literature, but I'm sure it's there. Okay, so monotonicity. Let me get rid of this clutter. I'm going to prove here in a minute that monotonicity, just by itself, implies that one does strictly worse in terms of distance to the optimum when taking a positive step, not a negative step. Okay, along the vector field, so along F. All right, so let's prove that, and then we'll think about the consequences of that. So first of all, why would you ever do this? Well, you probably wouldn't, but it's going to lead to a cute idea. Okay, so i.e. I plus this is bad. It's a bad operator. If I put a minus sign there, that would be xt minus eta f of xt. That's what we just analyzed. We see that kind of works, but not quite. This is going to be bad for both of our two diagrams. Okay, clearly from the one where the arrows are pointing in, this goes out. All right. All right, moreover, from the point of view of this diagram, think about what's happening up here. Here's F. If I'm right here and I take any size step, A to F, here, I'm getting outside the circle. So I'm diverging. Okay, and so if I do that again, I'll even go further out, it will actually diverge. So this is a bad operator in both cases. So that's interesting. We found something that at least unifies the two cases. Yeah?
So in which direction would minus F go here?
Sorry?
In which direction would minus F go here?
That direction. I know, it also, but that step would work well in the arrows coming in direction. I want to find something that doesn't work in both cases. It's kind of a weird backwards thing to do. Instead of find something that works in both cases, try something that doesn't work. And then we'll have a clever idea to fix that. You know what it is?
No.
All right, well, I'll try to get someone to guess here in a moment, just as soon as we do finish this little proof. So let's just show that this is true. So just using monotonicity. So if we take x plus eta f of x, and we subtract off y plus eta f of y, square it. That's equal to x minus y quantity squared minus twice x minus y eta f of x let's pull that eta outside. Eta f of x minus f of y. Bang. And then plus eta squared f of x minus f of y, quantity squared. Okay, and so by monotonicity, this thing is 0. And if we now ask, did we get further away when we apply these operators to x and y? Yeah, because the original distance was this, and the new distance is this plus a positive term. So we got further away. Yeah. This is 0 by monotonicity. Yeah. Okay, so anybody have an idea about how to use that fact, that we got an algorithm that fails in 2 cases? How could we use this to make something that does work in these 2 cases? There you go. Can you invert that operator? So we know if we go in this direction, and forward in time, if you will, it fails. So just go backwards in time. Okay, so that's the idea. So instead of y is equal to x plus this, just turn it around. So this is equal to what? I plus eta f applied to x. All right, so instead say, well, let's let x equal to I plus eta f inverse applied to y. That's an algorithm. Okay, if you give me a y, I can apply it to x, and that's going backwards. All right, so by the argument I just gave, this algorithm is actually going to make progress on every step. Okay, just under the assumption of monotonicity. Okay, so how can we turn that into something that looks like an iteration? So this is now the definition of the proximal point algorithm. So call y x of t plus 1 and call x x of t. Okay, so I get, x of t is equal to I plus eta f x of t plus 1. And now solve. So I'm going to get x of t plus 1 times this I is equal to x of t minus eta f applied now to x of t plus 1. Okay. Now, anybody see it? That's an algorithm. It's well defined mathematically, at least. Moreover, if I think about my 2 pictures, let's think about this picture. Here's x of t, and that is not x of t plus 1 out there. Okay, where is x of t plus 1? Yeah, pre-image. So where do you think it's going to be? Inside. It's inside. So it's a point such that, say, like right here, let's call this x of t plus 1. And what's the flow at that point? Well, the flow is that. And that flow is exactly what, I didn't draw it that well, but it's exactly what takes you from here to here. So you're kind of looking ahead. All right. So it's well defined, and intuitively at least it works. And if you now think about the vector field that's going in and the gradient case, it obviously works there. No issue at all. All right. So is there any problem with that? Sorry? You don't have to even say the word recursive. It's just a mathematical definition. There's another word in mathematics we use for things like this. Implicit. Yeah. So this is an implicit equation. There's lots of implicit equations in mathematics. There's not all that surprising. But implicit usually means we have to do a lot more work. We have to just solve some equation. This is not just equal, it's not explicit. All right, and solving this equation is kind of as hard as solving the original problem in general. Now, that's not true always. There are special cases where you can actually solve this, and that's where proximal point can just be used out of the box.
You don't want to call this backward Euler for...
You know what?
You don't want to call... This is forward Euler, backward Euler in the
Yeah, okay, so I was going to make that connection later, but we're not doing any continuous time analysis at this point. All right, but you're absolutely right that this is the backwards Euler, whereas the other one is Euler's, or if you think there's an underlying differential equation. And you should think that way, because right here, if I'm on this thing and I have a differential equation that says that's my flow, well, the differential equation will happily just go around that limit cycle. All right, it won't diverge. All right, and so I might think, well, okay, if I do a naive discretization, just Euler, would it work? Well, no, it's going to diverge because it was on the edge of stability. It'll start to diverge. But backwards Euler is more stable. All right, but what we're going to discover is that backwards Euler isn't just stable, it just doesn't stay on the limit cycle, it actually converges in. So it's even better than you might have thought. So differential equation thinking here at least doesn't quite help you as much as you'd like it to. And we're going to actually see that's a real phenomenon later. We'll talk about high resolution differential equations, which actually allow you to understand this better, not just ODEs. All right, anyway, that was a bit of an exotic step, but anyway, it is forward and backward in time, but in the time on the computer, we can define it however we want to. So we're, in some sense, we're going backwards in time, but we can do that. No reason not to. We just index in a different way, and we're in the algorithm this direction. Yeah, so I want to now prove that this works. And the proof is simple, but I want to you'll start to see the ingredients and then learn how to do this in other general cases. And then we will return to the fact that this is not really yet an algorithm. It's kind of a framework, it's an idea. And so let me answer your question first, then I'll tell you.
How big the step size can be? Because it seems like if you would make it very big, you would leave the circle.
No, it turns out that you can set eta to infinity, and if you set eta to infinity, you hop immediately to the fixed point. Okay, it's a super algorithm to have eta equal infinity. Think about that for a minute, but it's true. All right, the other thing to note is that this operator here has a name. Anyone know what that is? It's a resolvent or von Neumann expansion. Okay, so yeah, you could imagine taking the expansion of this as a formal power series, and you'll get all these terms, and you could imagine truncating it and getting kind of more of a classic algorithm. Okay. Anyway, this thing is often more well behaved than this in various branches of mathematics. All right, so let's do a proof that proximal works, and that'll be a starting place for getting algorithms. Let me just tell you what extra gradient is at this point. So extra gradient is an algorithm that is really implementable, very, very simple. And all it's going to do is it says, I don't know what x of t plus 1 is. All I'm going to do, though, is find an approximation for x of t plus 1. All right? So x of t is out, x of t somehow is out there. What I'm going to do is I'm going to start where I currently am, and I'm going to take a gradient step, pretend to take a gradient step, and go out there a little ways. All right, that point then is kind of partway there. I'm going to use that as the x of t plus 1 and then take another gradient step from there. So it's two gradients. It's called extrapolated gradient. All right, and the fact that we can prove that that works, and in fact the amazing part here, which I will get to, is that the extra gradient algorithm, even though it has this seemingly kind of little trick or hack in it, this approximation, is not only well justified, but it gives us a rate of 1 minus the condition number, not squared. So it actually improves over the thing we were doing before. All right, so that's where we want to get to. Let's see if I can manage to do this. Okay, so yeah, just as usual, we start with this and we start seeing where it goes once we start expanding. So same kind of argument. Not minus f of x star, because f of x star is equal to 0, and I'll explicitly be using that. Okay, good. Now, this is kind of good, telescoping sum or some other control. This I don't know. Probably I want to combine this with this somehow. All right, and this kind of starts to look like it's ready to go with monotonicity. Okay, I mean I could put that minus f of x star back in and it really looks like it, but that's a t plus 1 and that's a t. That looks like a problem, but it's actually, there's where all the advantage is. Okay, so what do you think you should do now? What do you do in mathematical derivations when you've almost got something you want, but not quite? This happens in statistics all the time. You add and subtract. Every field adds and subtracts. It's called the Pythagorean Theorem or something like that, I think. All right, so let's add and subtract something that makes this fit some of our assumptions. What would do that? Well, if I had an x of t plus 1 there, it'd be good to use one of my assumptions. So let's add and subtract x of t plus 1 into this. So this is now equality, x of t minus x star minus 2 eta, and I probably can't do it in my head on the blackboard, so let me write down from my notes, minus 2 eta f of, I can do this one in my head, x of t plus 1 minus x star then minus 2 eta f of xt plus 1. Let's see, xt minus x star. Is that right? T plus 1, there we go, thank you. And then we still have this term. Okay, so I added and subtracted. All right, so by monotonicity, this thing here is greater than or equal to 0. Okay, so I have a negative sign in from it, so it's less than or equal to 0, so I can ignore it at the expense of an inequality. So I get this. Okay, now, anybody have an idea of what to do with this remaining term here? We don't have a lot of assumptions going for us. We got monotonicity, and that's really it. And maybe Lipschitz we're kind of willing to throw in if we need to. You could, but there's something easier to do right now. Yeah, the dynamics. Remember, always there's the dynamics lurking there. That's defining this whole flow. And the dynamics says the difference between this and this is just the flow. Okay, so that is minus eta f of x t plus 1. Okay, so I get minus 2 eta f x t plus 1, and then by definition this is f x t plus 1 plus eta squared f x t plus 1. All right, so that combines with this. Did I get something wrong? Eta squared here. Thank you. Very good. Yep. Yeah. So I'm going to get a negative 2 eta squared of f squared. Here's an f squared with an 1 eta squared, so it's a negative eta squared overall. So I get this x of t minus x star squared minus eta squared f of x of t plus 1. And I have a descent lemma. Right? I can see that the error from here to here is going down by some positive amount. And once I have a descent lemma, I'm kind of good to go. I know I'm moving in. And I'm not doing it by adding some ad hoc, decay or something like that. It's just the algorithm naturally is doing that. Please.
Just to make sure I understand, so your monotonicity hypothesis, it works for the circle, but for an ellipse, it's not going to work.
Depends on what you mean by an ellipse. What flow?
The flow is, you have a stationary point.
Yeah. I think it will work there.
But sometimes you go away.
Yeah, good point.
How generic?
This isn't generic for any monotone operator. I just have to think whether that's a monotone operator there. I have to try to think that through a little bit.
even if you have limit cycles around the point, you think that generically you get ellipses?
You know, again, I don't want to think of these as the flow determines my dynamics. I want to think about what's the property of the operator. Okay, if it's a monotone operator, it's kind of a topological assumption about the vector field. And if I just have that, then the proximal point algorithm that defines the dynamics, right, will converge to the fixed point, to a fixed point. So I could stop and try to kind of think that through a little bit, but let me not, because I got so much to do. But let's kind of put that on hold about what vector field would we like to define. We're not starting with a differential equation and all that. We're starting with what is a natural monotone operator like Nash or something like that. Okay, so now we have a descent lemma. Descent lemma is not quite a rate. It says you knock off some amount, but it doesn't kind of quantify exactly how much you knock off. And so we could get an actual rate here, and we will actually with extra gradient. But let me just say that if we now further impose strong monotonicity, which we don't really need for convergence, but if we want to get a rate, it'll easily give us a rate. So if we add in or further assert strong monotonicity, then I want you to do the, wait a minute, is this what I want? No, let's not even go there. I think that'll just take me a little bit further afield. This would be a fun exercise for you to further impose that and actually see what rate you get out. I'll let you do it. I think it's not that as important in where I'm trying to go to. Okay, just let me give you a little bit more language if you want to read more on this. So this operator is often called the backward operator, kind of where it's like backward Euler. So this operator, I plus eta f and then an inverse applied to x, that's called the backward operator. And B is non-expansive, and that's what that proof basically shows, that you go downhill in a certain norm. And it's also what's called firmly non-expansive. Firmly non-expansive is a strengthening of expansive, or of non-expansive. And so I'm going to write that out, and it's a little exercise again to prove that this is true. So if I look at what B does to x and y, does it move them together? Does it move them further apart? If I put less than or equal to x minus y squared, that would be just a statement of non-expansive. Okay, this adds another positive term in here, which is I minus B x minus I minus B. So it puts in this other operator, I minus B, and applies that to x and y. That gives us another positive contribution, and now we're still less than or equal to x minus y squared. So that's firmly non-expansive. And there's a picture here, which is that if this is x of t, and this is x of t plus 1, this is what B does. B moves you from here to here, so B of x of t moves you to x of t plus 1. That's what the backward operator does. All right, and if I take the operator 2b minus I, so B moving from here to here, if I take 2b minus I, you can sort of think about it's a reflection. So it moves you all the way over to here. So this is what 2b minus I does to x of t. All right, and you can sort of see by the picture, and you can now easily prove it, that moving all the way over to here, this operator is non-expansive, but it's not firmly non-expansive. Whereas B is firmly non-expansive. It kind of moves in a little bit. Okay, so 2b minus I is firmly non-expansive. Yeah.
I'm having some issues with the backwards. The picture of the set on the top, on the blackboard on the right.
Yeah.
the last of the equations you just cancelled.
Yeah.
How is it that xt plus 1 is like on the left side of xt and not on the right side? Because down there, yeah, you just cancelled it, but it was written xt.
Yeah, I mean, this is f right here, not negative of f.
Non-negative of f.
Not the negative. This is the f itself. Okay. Okay, and so there's a theorem that you'll find in Boschke and Combat, which is worth knowing. It's a characterization theorem, which says that if you have any firmly non-expansive operator, not just our backwards hen, it corresponds to a particular monotone operator and its backward operator. Sorry, yeah, no, that's it. A particular monotone operator and its backward operator. Okay, so you find we're playing around in the functional analysis world of firmly non-expansive operators. One of you have come up with one, and you prove this little statement here. It holds for your operator. Okay, I, in principle, can go out and find a monotone operator, and its proximal point algorithm is your operator. So it's an if and only if. Okay. I skipped over a little bit, something more, but that was just kind of to tease your mathematical, this is what Boschke and Combat and some of these other books kind of get into, and the idea of resolvents and these operators, and there's a lot of characterization, so a lot of good stuff to learn about. So I'm going to now go do the extra gradient algorithm. Extra gradient algorithm, I do want to give a name to this one. I haven't been given lots of names along the way, but this is Korpelovich. I'm not sure I spelled it right, and I think this is like 84, but let's not put a date. And I do want to highlight that Korpelovich was female. She was living and working in Russia. And does anyone actually know her? Did any of you ever, the older people in the room? No? Yeah, so interesting person who wrote not that many papers, but wrote this particularly important paper. And I think she was at Moscow State University, and I don't even know who her ancestors were. But she came up with this really neat idea. Actually, before I get there, I want to make more point about proximal point. I will mention a name. Proximal point, in the way we're talking about it, was defined and studied by Tyrrell Rockefeller, in an important paper, again, I think in the 80s. And before that, people had talked about proximal point ideas, but just for in the optimization setting, where it was kind of like just a mathematical tool. It was just not really, like I said, like in Amir Beck's book, it's not going to be practical, so let's not even bother about it. He was the one who realized this applies to this general class of monotone operators, which already existed in mathematics, and it allows you to solve fixed point problems in some generality. Okay, and so there's a paper where he does that. He makes that transition, and that's a very important historical paper. All right, so she had that in mind, I'm sure, and wrote down the following algorithm. Okay, so it's not quite complete, but this looks, like something, it's like the gradient algorithm or the forward algorithm, but it defines x of t tilde in a particular way, which is like this. Okay, so the picture somehow is kind of that you start at this x of t and you follow negative, in this case, negative eta of f, and you get out to this x twiddle of t. And at that point, I'm doing this equation first, so I get out to this point right here, all right? And then I plug in f out there. Okay, so now that's f, negative f, eta f, at x twiddle of t, and I use that as my update here. So I now move in this direction like that. So that's my final x of t plus 1. So this is not what proximal point gives you. Okay, proximal point is somewhere else on the diagram. We often put a hat over it to denote that. Let's just kind of put that there for a moment. X of t plus 1, maybe that's what proximal point would give us. All right, and somehow we want to prove that these things are close. All right, and the amazing thing is that you not only can prove that they're close, but this algorithm is somehow even better. That's kind of really amazing. Yeah.
Predictor corrector.
It's predictor corrector, and forward backward also. It's kind of implicit explicit together. That's right. Yeah, no, absolutely. I do want to make some of those connections. If you're in the world of ODs and all that, and then you go back and forth with numerical methods, I mean, I'm sure that's what she was. Probably a numerical analyst would be my guess, and kind of knew all that. Yeah, but it just turned out to be particularly useful for this non kind of ODE world. All right, so okay, so I've done my best to put down a proof here, kind of partly from memory, and I did it last night, and it does work, although at the end there's a little bit of hand waving. There is a recent paper where I looked at that afterwards, and I think it's a kind of cleaner, slicker proof, but just kind of different than the flow I had. And this is by, and I maybe someone could help me look this up. It's Mokhtari Ozdaglar, and I don't remember the third author's name. Maybe Nehal, you could help me with that or something, and somebody. Like a year or two ago, they're all at MIT, and they wrote a paper on proximal point, extra gradient as an approximation to proximal point, and also I'm going to mention optimistic gradient descent ascent, which is another approximation to proximal point, and they analyze both of them as like a unified framework for understanding these algorithms that people are using as instances of proximal point. Okay, so that's actually, don't look at my notes after today, look at that paper. I think you'll get probably a little better story. But again, they don't have that many pictures, so maybe my presentation will still help you. Okay, so the idea here is we're going to measure how far, all right, sort of measure the difference between extra gradient. At the end of the week, my handwriting gets worse and worse. I don't have a lot of practice doing handwriting, so. And proximal point in this way, in a certain way. Okay, so consider x twiddle t plus eta twiddle x twiddle, okay, minus x of t. All right, so let's kind of think of this as a figure of merit. All right, so if this is 0, all right, then you can see that x twiddle of t is actually equal to x hat t plus 1, and by this I mean what PP delivers, what proximal point delivers. Yeah.
Do you want the paper now?
Yeah, I do.
So the last name is P-A-T-T-A-T-H-I-L.
P-A-T-T-A?
T-H-I-L.
T-H-I-L, okay.
And it's 2019.
Okay, 19.
Yeah.
Google will find it from there for you guys. A very nice paper. They do it by the way in somewhat general convex concave, but they also do the bilinear game as kind of a special case. The bilinear game is x transpose AX, and they work it all out there in that setting. That's kind of a little bit of a nice Bohr atom. You can really play around with algorithms in that setting and really get some ideas. It's a lot of eigenvector kind of things, simple things come out of that. Okay, so if this turns out to be 0, then we really just redefine proximal point. So let's make this nearly 0. Maybe that's kind of what algorithm would make this thing nearly 0? Well, it turns out it's extra gradient. All right, so I think I can now try a full proof of extra gradient. This is the proof of extra gradient. All right, it starts as always. Okay, so don't need to belabor this. Minus 2 eta. Okay, so again, same kind of story as with proximal point. If we had an x tilde here, we would be able to use monotonicity. Okay, but we don't have an x tilde, so we add and subtract. Okay? And this add and subtracting is pretty important. It gives these terms that cancel in favorable ways. All right, so this is equal to xt minus x star squared minus 2 eta. Make sure I got all this right. Yeah, okay. F of xt twiddle minus x star. So I added it in and then subtract it out. All right. So we've kind of used, how do I motivate this last step here? So, all right, so we've isolated something here, which we can use our strong monotonicity on. Great, so we got that handled. We don't want to mess with that. And so somehow these two terms have got to combine somehow. All right, and the other trick, add and subtract is our favorite trick. The other trick we have in our bag, other than just using yet more assumptions with inequalities, is complete the square. What did you say? Use the algorithm is often a good trick, but here that's not going to help us. But anyway, complete the square. So we're going to put this together with this. We got something squared, and we have that thing there, so it looks like almost a quadratic, and it is. And then we'll use the algorithm. Are you already jumping ahead? Yeah, I think all right, so I'll just write the whole thing out. All right. We're not going to mess with this. We're happy with that. And you complete the square. So what that turns into is just xt minus xt twiddle minus this of xt twiddle minus xt minus xt twiddle squared. Okay, and you can, once we've written it down, you can easily check. Okay, so this is the new term. Everything else on this equation was present in the PP argument. So this is the new term that extra gradient is giving us. Okay, and it's a nice term because in fact it's just the algorithm. Actually, it's not quite right. It's not quite the algorithm. No, it's the error term that we want to use to measure the algorithm. It's what I wrote over here. It's that. Okay, it's something we'd like to make small and prove that extra gradient does that. Okay, so instead of keep writing everything out, I'm going to focus. Let's just focus on this new term for just a second. Do a little analysis with it. Okay, so that's just by the definition of the algorithm is equal to eta f xt, all right, minus eta f xt twiddle. All right, and now we do want to use Lipschitz, which has kind of been lingering in the background. If I'd stated the theorem, I would have put it in there, but let's bring it in now. So less than or equal to eta gets squared, we have L squared from Lipschitz, and then we're down to xt minus xt twiddle, quantity squared. Okay, and so now if I go back and plug that back in, we're going to get something good happening. And let me just note that Lipschitz is kind of clearly needed for extra gradient to work, because extra gradient is sort of saying I'm going to not use the F I really want to use out there. I'm going to use a slightly different one. And so if F were changing wildly in the neighborhood, we'd be sunk. So we really need Lipschitz. All right, so now returning back to the main thread, we've got less than or equal to xt minus xt star squared. Minus, okay, so, okay, in my notes I've done something a little, let's see. I wanted to go all the way to a rate, so I allowed myself to put in strong monotonicity at this point to keep this term not just zero. Let me just do that for a moment, and then I'll tell you what happens when that term is zero. So let's use strong monotonicity just for a moment. So this thing right here is by strong monotonicity 2 eta mu, and then our difference between the all right, now if this were, if mu were zero and we just have monotonicity, this term would just be vanishing. That's all. Okay, so let's add it in just to get a little more insight into what this algorithm can do. Also, if you allow strong monotonicity. Let's see, I don't want to erase that. Okay, so then I have plus the thing I just got right here, and then a minus 1. So I get L squared eta squared minus 1 times xt minus x twiddle t quantity squared. Okay, so now we're going to set, we now know what step size to use. We're not going to be able to use an infinite step size like we use with proximal point, which is not really a real thing to do anyway, but we could bound this, upper bound this by a very traditional thing to do, the Lipschitz constant 1 over L. Okay, because if we do that, then this thing will be negative. And if it's negative, we get ourselves a contraction. But anyway, let's go ahead and leave in this term just to finally to get a real rate. Otherwise, I would have this contraction, and I could work further to get rates for extra gradient without the strong monotonicity. But I wanted to put the strong monotonicity in and get a final rate here. So less than or equal to 1 minus 2 eta mu xt plus x star squared. Okay, and let me just say I'm cheating a little bit here, a tiny bit. All of these terms, it's a minus. We have xt minus xt squared sort of everywhere in sight, except here I have an xt twiddle. Okay, so I need a little bit of a triangle inequality there, and they'll give me a little bit of an error, but that error is controlled within what everything else I'm saying. And I just didn't have time last night to kind of write that out. And if I did, I think it would just be ugly. So I'm leaving you to kind of patch the last little part of the argument there. Okay, so this is a very nice contraction. Okay, and in particular, if I set eta to this, it's equal to 1 minus mu over L. So I get linear convergence with mu over L, not mu over L quantity squared. Okay, so when I put in the strong, strong monotonicity like strong convexity, all right, somehow extra gradient magically exploits that and gets you an even better rate that's reminiscent of the one back from optimization. Whereas proximal point alone doesn't. That's kind of interesting. And a proximal algorithm does better. Kind of interesting. All right, let me just pause for a second. I do have some more I want to do. But let me see if there's any questions. That was quite a lot.
Can I ask a question?
Yeah.
Why did measure the discrepancy between extra gradient and proximal? Because I should have asked you.
No, it's really, that's maybe not quite right to say it. It's, it's kind of measures how far this step, this extra gradient thing is away from where proximal would go, right? Because if this thing is, if this thing is equal to 0, then I have equality here.
Okay. Then it's
Yeah.
Okay.
Yeah.
So you could iterate to more extra gradients. Right? You could,
Yeah. Yeah,
If you
exactly.
do that, does that converge for any, does the assumption of monotonicity
guarantee that it converges for any value of eta? Because in principle,
Not for any value of eta. So eta will change. In fact, you've just rediscovered what's called the look-ahead algorithm, and it's due to Tatiana Chavdarova. She did have a paper on that a year or so ago. And so she looked at multiple steps of an inner loop and said, how many can I take, how much advantage do I get versus how much does the step size got to be diminished? And it's overall got some advantage. I'm going to actually mention that here in a moment.
In the very first analysis, why could it be set alpha to 1 over L? Is that because there was a factor of...
In the which alpha over whatever, in which?
In the very beginning, when we were talking about monotone operators,
Yeah.
we said alpha equal to mu over L squared.
Yeah, right.
In that analysis, if we said alpha equal to 1 over L,
Yeah. You're still going to get divergence.
then
Yeah, you'll still get divergence. It won't
That's
converge.
right.
Yeah, that's right. All right. Yeah, please.
Can you comment really quickly on the relationship between mu and L for a given function?
Between mu and L, that's the condition number. That's the condition number I talked about on day one. Yep. So take the quadratic bowl kind of thing, and that'll give you some intuition. Yep.
Can you comment just a little more on this strong convexity assumption? In a sense,
Strong monotonicity.
uh,
We're no longer in the convex world. Yeah.
parabola as well as the
Okay, that's back in the convex world. We can talk about that if you want.
strong monotonicity.
Strong monotonicity, yeah.
Because I understand why by using that you can have it, by using this predictor corrector thing you can convert inside. But is it like a natural thing to expect in this kind of problem that you think of, or is it really just that you need it for?
Yeah, that's a good question. I'm not enough of an expert to really say. I mean, you need to kind of be in the field for 20 years and sort of see how often it's helping you, how much it's not. I would say fairly often. I mean, I think there's a lot of problems. A lot of these are design problems, like an economist wants to design some aspect of the economy, and so they can kind of make it so. You will often see in economics papers, they will make that assumption because I think they think they could make it so.
So that's what you really need is like for these vector fields to be like a certain curve.
Yeah, so you can kind of do that. But as we were talking about the other day for like machine learning, it's a little harder to make it so because the data comes in and the data is the data. And so, if you knew the statistical model generating it, you could make it so, but you don't know that. All right, so let me, one more quick, yeah, sure. Yeah.
to connect with what you said before.
Yeah.
You told us how to minimize function. I could minimize f squared. Right? So, of course, that requires more cost and you need more assumptions. You
Yeah.
have gradients.
Yeah. I mean, so you can do lots of things here. This is definitely an open playground here to play around with. So, and in particular, you can take I plus eta f, this resolvent kind of quantity, and you can do an expansion. You get 1 minus eta plus eta squared, f squared, plus, blah, 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 and you can do that. And it will probably be better. The analysis will be hard and all that. But it will not probably be better in practice. And it's kind of this thing that you probably heard from the other speakers earlier this week, that the modern perspective, especially in large problems, machine learning, is do something cheap and get moving, right? Don't sit around and do something perfect and then take a step. Even though in principle, the number of steps would be smaller, but you just wait, it'll just take you too long on each individual step. So I think that's kind of true here as well. Okay, so let me tell you something about this high HRDE perspective. That's due to my group. So it started with Ben Shi, who was a postdoc with me, and then Tatiana has picked up on it, and Manolis Zampatakis. All right, so high resolution differential equations. It's not a complicated idea, and I'm going to just introduce it in the context of the minimax problem. So let's do this for minimax optimization. Okay, so min, max, xy, f of xy, which is a convex concave function. Let's let z is equal to xy vector, just put them together. And then in this notation, v is, let's call it f, that's what I've been calling it all day. F is equal to del x of fxy or fz, and then minus del y of fz is the other component. And then let's get a Jacobian as well here. So del squared x f of z, del squared y f of z, del x del y f of z, and then minus, and that should be a minus 2 minus del x del y f of z. Okay, so second derivatives and first derivatives. All right, and so let's look at some methods that one could try to use to find a saddle point of convex concave functions. So it's a special case of our variational inequalities, but really interesting and important in real applications, special case. So there's something called gradient descent ascent, all right, which I didn't really talk about, but it's kind of obvious, is that player one wants to go downhill, they take a gradient step downhill. Player two wants to go uphill, they take a gradient step uphill. And people do this, and you know, in the neural net people with GANs and all that stuff, they try to do stuff like this. And it doesn't really work very well, but here's the algorithm anyway. It looks like this. Zn plus 1 is equal to Zn minus some step size f of Zn. Why am I using n? I think it's because on our paper it was n, but let me put t, and that's what I've been doing all day. T. All right, so it's the obvious thing. Now, because f, remember, has got the two components. One's gradient, the other is a negative with a gradient. Okay, so putting the two together is gradient descent ascent.
Will you do them simultaneously here, or
You do them simultaneously here in this algorithm. Yeah. You could do it more sequentially as well. That's a slight variant. It doesn't converge either. So GDA, extra gradient, is now we can write out in a nice kind of compact notation. This is what you'll actually see most in the books presenting extra gradient. They'll write out this, and like I say, they probably won't give you a lot of intuition. So ZT minus gamma of f of ZT minus gamma of f of ZT. Okay, so there's the ZT twiddle, but you can write it out in one equation like that. Optimistic gradient descent ascent is kind of a favored algorithm by some people. Let me mention another name. Kostas Daskalakis is doing some very nice work. Kostas Daskalakis at MIT. Daskalakis on convergence properties of these kind of algorithms, and he tends to work with this algorithm. So ZT minus 2 gamma f of ZT, and then outside of the parens, there's a plus gamma f of ZT minus 1 now. So this has got a little more flavor of a lagging or momentum kind of method. And then the look-ahead method, which is due to Tatiana Shavdarova and other people, is ZT plus 1 is equal to ZT plus alpha, Z twiddle. Now this is a twiddle, this is a different variable, so this is T plus K minus ZT. Okay, so let me,
Sorry, the optimistic is
Yeah.
ZT minus 1 for the last one?
ZT minus 1 for the last one, yeah. And I that didn't look right to me. There should be an F in there somewhere, but I don't know. Huh? Anyway, this guy right here is gotten by taking K steps from where you are using a base algorithm like gradient descent ascent or extra gradient or something like this, and this kind of corrects for that. So let me not get into details here, and I'll try to patch that equation if that's not right. Okay, so now which of these is better and so on. Well, this one you can sort of show diverges. We did really show that earlier on. We just did different notation. And these three all have nice convergence properties, but are they which is better than the other? And can we really analyze the differences among them? All right, and so it's hard. And in discrete time, it's pretty hard. And we might hope that going into continuous time, just like we saw for optimization and acceleration, all that gave us insights. All right, and so you can start by doing that. You can take each one of these equations, and you can take the step size to 0 in the traditional way and get an ODE. All right, you can do that. It's not hard at all. And what will happen is that all four of them will collapse to the same ODE, and it'll be the ODE associated with this bad algorithm. Okay, oops, we get no help on understanding these new things from going to ODEs. All right, so we kind of knew that already from working with optimization problems, where we started to work with this idea of high resolution differential equations. And since my time is minimal here, let me just give you the intuition. You can read the paper. It's actually not that hard. We have some kind of a algorithm, x of t plus 1 is equal to something, some operator g on an x of t, and then there's a step size gamma. Okay, somewhere incorporated in that operator is a step size gamma. All right, so we have gamma, and then we also have a discretization, which is that we say, well, what's happening here is that there's an underlying, let me use n here now to kind of distinguish between time. And so we say that, x at time t is equal to x of n delta for some, delta. All right, and so we then take delta to a yellow grid of deltas, and we take delta to 0. All right, so, in classical difference equations, this would be quite natural. You take this, you get the ODE. But we do have this extra variable here. So what do you do with that? And the usual thing is in some ad hoc way just to kind of, as this is going to 0, take this to 0 as well. Maybe set this equal to this. That's usually the common thing to do. And that's one way to get an ODE. All right. This way, which comes from fluid mechanics, says no, treat both of these equations as having this variable delta and gamma, and do Taylor expansions on both of them. Get something in delta, delta squared, delta cubed, or whatever, and do the same thing with gamma. Gamma, gamma cubed, delta squared, gamma cubed. All right. From those Taylor expansions, right, you can take limits, and they don't have to be the same limit. You could set gamma equal to square root of delta. Very interesting, useful thing to do. And you will get out different limits, and they will be all ODEs at the end, but they will be called high-resolution ODEs. And they give you different perspectives on the underlying dynamics. So like I say, in fluid flows, this is just done all the time. This is very, very, very common. All right, so we did that in this recent paper written about a week ago. It's on the archive, and I'm just going to show you, it's a fun analysis to do. I encourage you to play around with this technology. We get out the following algorithms. So they're all written in phase space. So there's going to be a variable z dot, which is the z from over there, but now in continuous time, and it's got, there's this variable z, and its derivative is at omega, and then the rest of the equations all just work on omega. So gradient descent looks like this. Omega dot is equal to minus beta omega t minus beta f of z of t. So that's the ODE that comes out, and you can analyze that ODE, and it's kind of a bad ODE. It's going to diverge, okay, interestingly. It's not surprisingly. What about extra gradient? What's the high resolution differential equation coming out of there? So it's omega t is having the same first term and the same second term, f of z of t. And then there's a correction term, an additional term, and it has the Jacobian in it. So plus twice the Jacobian of z of t dot the flow, z of t. Z of t, time, continuous time. Okay, so that's a different differential equation. OGDA has something similar. All right, minus 2 Jacobian z of t omega of t, not z of t, not f of z of t. And then the look-ahead algorithm, look-ahead 2. So you set k equal to 2, you get this explicit dynamics. It had this extra parameter alpha in it, so it comes out there. F of z of t plus 2 alpha Jacobian of z of t, f of z of t. All right, so those are fresh off the press, and a bunch of interesting observations. First of all, you can analyze these things with, Lyapunov. Secondly, OGDA, which seemed very different, it looked at a ZT minus 1, and it kind of had this momentum flavor, is not very different at all. These two terms match, and these two terms are closely related.
Can I just ask?
Yeah.
How does beta go back to? Is it
Yeah, beta was the, oh gosh, what is beta? It's getting late in the day. My brain's a little fried right now.
next question was, you said basically these come up as different scalings between gamma and delta, so maybe...
Right, so it has to do with that. I'm just forgetting the exact detail. Yeah, I mean, it's a maximal value. Any smaller value is also defines the same dynamics. I forget exactly how it's defined. All right, so anyway, these terms over here are obviously key to getting the convergence. And we kind of learned about that when we talked about the symplectic surgery methods the other day, that they had incorporated this extra term. But the fact is they aren't calculating explicitly the Jacobian. It's just the fact about the dynamics. It's kind of implicitly using Jacobian type information. Okay. So anyway, this is at the very beginning of this line of research. There's probably going to be a bunch more papers on this. I hope there will be. Analyzing these things, finding how fast they converge in continuous time, knowing how to discretize them, blah, 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 all the kind of things we learned how to do the other day.
Is it also minus because omega t or plus omega t?
Here, should have been minus. Thank you. That would have been a wildly different algorithm. Okay, so it's 5:30, so I have done my nominal time. I did not get to contract theory and to matching markets, and that's fine. If you want to learn about that, I have given now several talks in the last 6 months on that, and you will find them on the internet. So you'll just see what I would present here. Let me just say a couple of minutes about what they are. Maybe just the, yeah.
The beta is inverse step size.
Inverse?
2 over the step size.
2 over gamma?
Yeah.
Thank you. So we had a couple of interesting lines of research that I, in a fourth lecture I would do. So one of them is to consider building markets where there's kind of producers and consumers that want to be matched to each other, and they don't know their preferences for the other side a priori. In economics, you assume the preferences are known, like I want to go to this college and this college and this college, and everybody does that, and all the colleges rank their applicants, and then there's a matching algorithm someone got a Nobel Prize for, okay? And it's used for kidney exchange markets and all kinds of other very important important things. In lots of real life situations, we don't know our preferences a priori, all right? So in machine learning, we have these ideas of bandit algorithms. Right, where I try each one of the arms several times and I start to form preferences based on the rewards I get. And there's regret analyses and optimal algorithms and blah, 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 blah. All right, so we have a line of work where you put together those two ideas, matching markets with bandits, and prove all kinds of theorems and get optimal regret, and even we get a new Lyapunov function that the economists will probably be able to use for their purposes as well. So that's one line of work. The other line of work is really hot off the press, and it's probably the thing I'm most excited about, so I just did want to mention it. We call it statistical contract theory. And the motivating use case is where there's a principal. In contract theory, you have a principal and you have a bunch of agents, right? The principal wants to get the agents to do something, but the agents know things the principal does not know, and they're not willing to reveal that, like how much they've studied, how healthy they are, how fast they can work and all that. I want to motivate them, but I can't get them to, so I'd like to give them some money to do something, but I don't want to give them money when it's useless, because they would work harder, they don't need the money. All right, so contract theory talks about problems like that, and you all know the kind of classical example of the airplane having business class fares and economy fares. So why do they do that? Well, everybody is happier in some sense. The plane is full, plane's happier, and more people fly than would have otherwise been the case. So how does that work? Well, if you were just to set one price for every seat, which is seems democratic and all, right? Then what happens? The airline has got to set a price, say 100 euros, right? And there's people who would pay a lot more than 100 euros for that flight, but they say 100 euros, grab it, and they pay only 100 euros. So the airline lost the income they could have gotten from those people, all right? On the other hand, if they set it, really too, a little bit too high to try to recoup some of that, then the people who don't want to pay 100 euros will not, and the airline will be half full. All right, so you all know what's done. So you'd like to maybe price discriminate. You come in, I say, I'm going to go to Rome, and I look at you and I say, well, how wealthy are you? How much do you want to go to Rome? Your price is going to be 200 euros. You can't do that. It's illegal and socially unacceptable. All right, so instead what you do is you say, here's what I'm going to do. I'm going to set up two prices. There's going to be something called business class. And in business class, you get an extra little cup of wine, and you get a little bit more room. And you'll pay 1,000 more euros for that. Now, that seems crazy, but there are a lot of people who really want that prestige of sitting in that bigger seat and having that cup of wine. All right? Now, you're not smiling because none of you would do that. You think it's just ridiculous. But there are people who do this all the time. All right. So the airline then gets that higher price from people who are just willing to pay it for this little extra distinction. All right. And then the lower price for the economy people says, I don't want that stupid glass of wine. All right. And then you can make mathematics out of this. And that's what contract theory does. And in contract, my favorite book on contract theory is Lafont, Laffont, and Marty Moore. It's called The Theory of Incentives. A very beautiful book. All right, and so they set up mathematics that allows you to treat problems like this and figure out how the menu of prices to use. Price and service. So this is, filled the world of economics for like 20 or 30 years. So our application of those kind of that way of thinking is it's more statistical. So we imagine the Federal Drug Administration, FDA, is trying to get drugs to market. All right? They're the principal. There's a bunch of drug companies who are trying out various drugs, and they want their drug to go to market. They'll make money. Now, the drug may or may not work very well. A lot of drugs just don't do anything to anybody. They don't work. Some other drugs do work. So the agents know a little bit about that. They didn't run a huge clinical trial costing millions of dollars, but they did a little bit of sampling internally, and they have maybe some good people, good chemists, and they could kind of figure out, oh, my drug, I think it's really going to work. All right? But no one really knows. So they ship it to the FDA. The FDA spends tens of millions to hundreds of millions on clinical trials. We know about this for the vaccines. All right? All right, now, but there's some false positive rates. Even though I'm running these big scale trials, there's a chance that even though the drug doesn't really work very well, I try it out on my clinical trial, it looks like it worked. False positive. That's what we get in statistics all the time. All right, so then I release it to the market, and that person there makes billions of dollars. So they're incentivized, highly incentivized, if they're pretty not sure or they even think it doesn't work very well, let's go ahead and try it out. Get no loss. Okay, so the FDA knows this, so what they need to do is set up a menu of options. All right, they can't ask you, does your drug work? What do you know internally? Just like I can't ask you, how much are you willing to spend on the flight? All right, so we put up a menu of options for them, and it's sort of how much they have to pay to play the game. You want your drug to be tested by me, the principal, you got to pay a little bit, $50,000. All right, and so that starts to cut down the incentive. So you can work it out so that you can do Neyman-Pearson style testing, controlling false positive and false negatives, but doing it in an incentive-compatible way with this hidden knowledge. Okay, so there's a new theory of that and new algorithms, and it can be used in the federated learning setting, where you're trying to build a central model, your Google or whatever, you're collecting all this data from all kinds of people on the edge, that's called federated learning, but that work has not been done with any notion of incentives, which is kind of crazy, because how do you incentivize people to actually send you the data, or not to send you false data, or not to do blah, blah, blah? All right, well, this theory applies to that setting. Okay, so that's something I'm particularly interested in and excited by. The contract theory people had no statistical data analysis in it whatsoever. It was just, everything was assumed known, and you worked out some prices. All right, so I am totally finished. That was enough. I think so happy to hand